Hi, everybody. This is the second talk of the evening. So this is generics on the Java virtual machine. What you don't know will most definitely hurt you. So just get my slides sorted out. Here we are. So my name's Garth Gilmour. I was a full-time software developer for about 6 years. And then the opportunity came up to give this a go. And terrifyingly, that was in 2001. So back of an envelope, I've done about 1,000 different workshops and training courses and conferences and all that kind of thing. And I'm the head of learning, the chief trainer for a company called Instil. We're based out of Belfast. So about 80% of what we do is software development, but we also do consultancy and training as well. And the consultancy and training wing is louder than the rest of the company. So that's how most people encounter us for the first time. And these are a bunch of people that we've worked for. So a quick shout out before we begin. We run a user group in Belfast called BASH. In the beginning, it was just BASH, and then people started saying, Belfast Association of Software Hipsters. And we went, yeah, that's what we always meant. Really good. So once a month, we pick a topic in computer science, and we have 2 or 3 really good speakers. So we're doing those virtually now. They're online. They're worth a look. And we also host the Belfast Kotlin user group. So if you're interested in presenting there, just let us know. You'd be very welcome. So the agenda for this talk, it's really generics in 3 acts. So in the first act, we'll make clear the existing issues in Java. In the second act, how Kotlin simplifies these and mitigates against them even. And then in act 3, some of the fun things that await us. You know, some of the fun ways that generics could be extended on the JVM for all JVM-based languages. So let's start out with a definition, always a good idea. What's generics? Well, this is from a tremendously good presentation by Ted Neward on advanced stuff that you can do with TypeScript. So if you have any interest in TypeScript at all, really great talk. And I love his definition. Generics are those things that hurt people. Okay, so why should generics be so bad? Well, continuing with his talk, it's extremely hard to debug a type system. In other words, we can write regular code and we can attach a debugger to it and step through it and so on. But whenever you're working with generics, there's stuff going on at compile time. So things are being understood and mapped and transformed and so on. And we have to kind of mentally visualize what's going on inside the compiler. And it's not really something that you can debug into. So that makes generics particularly hard. So as you know, of course, in the beginning, Java and C# lacked generics. You could still do generic coding with a lowercase g through using references of type object, but that didn't really give you type safety. So they added it to both languages, but they went off in different directions. And they were both right, yeah, because in the case of C#, it was a relatively new language, and they weren't too worried about breaking backwards compatibility. In the case of Java, it was a much more mature language. They had billions of lines of code out there. So the last thing they wanted to do was break backwards compatibility. So they went different ways, but they were both right, you know, that they were both following the correct path. So whenever they added generics to Java, it was first prototyped through a language called Pizza. Yeah, and Martin Odersky was the main person there, who of course then went on to develop Scala. So if you're not familiar with Pizza, it's well worth your time. So I would refer to you this tremendously good talk from Go to Copenhagen back in 2019, which goes into detail about how Pizza prototyped many of the features that we now enjoy in Java and Kotlin and Scala and so on, and even some features that are still to come. So a brilliant talk, well worth your time. And then just in terms of background reading. So white paper, I always recommend Generics in the Java Programming Language by Gilad Bracha. That came out in 2004, just before Java 1.5, just before they added generics to the language. Really good paper. And then another one by Brian Getz from this month, you know, so really, really good paper again discussing why they went the way they went with generics. And then if you really want to get into it, as maintained by Angelika Langer, there's the Java generics FAQ, which comes in, last I checked, at over 350 pages. Yeah, so you're not going to get through that in a single evening. Okay, so that's something that you just want to dip into. But the sheer size of that should give us some idea of the complexity. So, you know, Act 1, let's just explain where the complexity comes from. So we'll take the class hierarchy that everybody uses. We'll have director extends manager and manager extends employee, and let's have 3 linked lists. So we won't bother about interfaces. We won't use lots of collections. We'll just pick one concrete type, and that's the linked list type. So emp list is going to be a linked list of employee, manager list, linked list of manager, dir list, linked list of director. And let's say we've got this function here, Q1, and we're passing in a linked list of employee, and we've got these 3 calls here, A, B, and C. So A, we're passing in the emp list, B, the manager list, C, the director list. Yeah. So if you ask a bunch of Java or Kotlin developers without them knowing it's a trap, which of these will work, they'll say all of them. Yeah. But of course, if you've played with this before, you'll know that only A will work. Okay. And what's the reason for that? Yeah. Well, because inside Q1, we might want to add an employee. Makes sense. It's a linked list of employees. So to a linked list of employee, we'd like to be able to add an employee. But note that if we let calls B or C go through, well, then we'd be adding an employee to a linked list of manager. We'd be adding an employee to a linked list of director. So we don't want to be able to do that. Okay. So it turns out that only call A is allowed to go through. But then if we look at this code here and say, okay, so let's say we call this function here Q2 and pass in a linked list of employee, what will we be allowed to add to it? So again, most people, having seen the one before, they'll go, aha, only an employee. Yeah. But it turns out that all of these will work. Okay. And why would all of these work? Well, because it's a linked list of nodes, and each node contains a reference of type employee. Okay, so this is Java, and we're working with reference types. Objects are always accessed through references, and you have the apparent type of the reference versus the inherent type of the object. So the reference can be of type employee, but the object can be of type manager, and so on. And that I find is really the problem with generics, okay? So the problem with generics is not understanding type parameters themselves. The problem with generics is that in Java or Kotlin or Scala or whatever language you're working with, you're juggling the rules of type parameters, and you're juggling the rules for inheritance and object orientation, and you're juggling the rules for reference types, okay? So if you like, there's 3 balls in the air, and you have to keep juggling them, yeah? And sometimes your intuitions in one direction will send you the wrong way, yeah? So your OO intuitions, yeah, can send you badly in the wrong direction whenever you're thinking about type parameters and so on, yeah? So it can be incredibly difficult to juggle these things at the same time. There's a lot of cognitive dissonance, there's a lot of interference that goes on. So that's what makes generics particularly hard. So going back to our questions, looking at this code here, which of these will work? Well, here we're using the wildcard, okay? We're using the question mark, and all of these calls will go through. Yay, okay? But then the problem is, what happens if we try to add anything? We won't be allowed to, okay? So we can pass in a linked list of anything, but we won't be allowed to add any kind of object. We won't even be allowed to add, call D there, a new object. That trips up an awful lot of people. A lot of people think that should be possible, but it's not. So the reason why all of those fail is that the question mark doesn't mean anything works. The question mark means of unknown type, okay? So we're saying to the compiler, please willfully forget everything you know about this type. So because we're forgetting what we know about the type, we won't be allowed to add anything at all, yeah? And again, people internalize the wrong rule. So a reference of type object can point to anything, but that doesn't mean an instance of the object type is acceptable everywhere, okay? That's a subtle distinction that can trip people up, okay? So yes, a reference of type object can point to anything, but that does not mean that an instance of the object type is acceptable everywhere. So that's another common trap that people fall into. So that's not the complicated stuff. That's the prelude, okay? So where the wheels really start falling off the cart is whenever you start getting into the bounded wildcards, okay? So you see here, we can say question mark extends manager, yeah? So T is either manager or something that extends manager. So in this case, calls B and C, they should proceed, they should go through. And then if we try and add something, Well, because we've said T is manager or something that extends manager, you'd think that we could say new manager or new director, but we can't, okay? And it turns out that all of these fail. And this was the really big thing that stumped me whenever I was personally learning generics. And it wasn't until I read a tutorial where they said, look, the set of possible values for T here is actually infinite. In other words, if I wanted to, I could devote the rest of my life to creating classes which extend from manager or director, okay? Wouldn't be a particularly good life, but I could do it, okay? So let's say after we write Q6, I go out and create classes like CTO and CEO, which extend from director, and then I can call Q6 and pass in, for example, a linked list of CTO, you know? So to a linked list of CTO, I shouldn't be adding a regular director. Okay, so because the possible set of values of T is infinite, I'm not allowed to add anything. Now we could go the other way. We could say question mark supermanager. Yeah, so now T is either manager or employee or object. Okay, so if we do that, then A and B will go through, and we know for sure there are 3 possibilities for T. And that will mean that we can add things, okay? So it kind of confuses people that we can add things, especially that we can add a director. But if you think about it, what are the possible circumstances that we could have, okay? What are the possible values for T? Well, we know that T is either manager, employee, or object. So can a reference of type object point to a director? Yes. Can a reference of type employee point to a director? Yes. Can a reference of type manager point to a director? Yes, you know, so we're all good. Yeah. So for all 3 possible values of T, it'll work, you know, so we can allow the adding of a director to the linked list. So just thinking about what we've learned so far, yeah, generics and inheritance hate each other. Okay, that's the big lesson I'm trying to get across. Okay, so you know, generics, grand. OO, grand, until you include inheritance. You know, so once you start mixing generics and inheritance together, it all gets very complicated. And our OO instincts will send us the wrong way a lot of the time with generics, and everybody finds these bounded wildcards confusing. They don't work the way we want, okay? It also doesn't help that you've got 3 kinds of terminology, okay? So we're saying extends, but that's an upper bounded wildcard, okay? So extends means upper, yeah? So how do you get used to that? Well, the way I like to think about it is that assuming you draw inheritance trees the way most people do, with the base at the top and the derived underneath, well, whatever T is, you go up to go to manager, or you stay the same. And then if you use super, well, that's a lower bounded wildcard. And the way I memorize that is that you go down to get from whatever T is to manager or stay the same. Okay. So just while we're talking about, you know, this, as an educationalist, as somebody who teaches people, the or stay the same bit causes no end of confusion, okay? So we do have language designers on the call. This is great, yeah? So please let me appeal to you, do not repurpose keywords, okay? No good ever comes of it, yeah? So we had a wonderful example of this the other day. In C++, whenever they were doing generics, they needed a keyword to introduce a type parameter. So you can't just say T or U, yeah? So what they did initially was they repurposed class. So if you've done C++, you'll know that one way you can introduce a type parameter is by saying class T. Don't, okay? So that they did this initially, and it confused the hell out of everybody. So much so that they introduced a new keyword type name, and that's what you're supposed to use. But as you can see from this little Twitter poll, which went out a few days ago, even now, 20 years after they've done it, almost 13% still prefer to say class T. So this was my comment here at the top. Please don't do this, okay? This will confuse the hell out of students, yeah? And you can see below, this gentleman here very kindly backed me up, you know? It causes nothing but confusion. So please, whenever you're designing or extending a programming language, don't repurpose keywords. You know, it's a very, very bad idea. So we've said that you can say extends, and that means upper, and you can say super, and that means lower. But then we get the computer science terminology, because, you know, the wonderful thing about standards is there's so many to choose from. Yeah. So if you're using the upper bounded wildcard, that means covariance. If you're using the lower bounded wildcard, that means contravariance. Yeah. So if something's covariant, then we can extract. If something's contravariant, we can insert. and people are forever coming up with little diagrams. Here's a particularly nice one here to try and explain what that means, but it confuses everybody. So in the world of Java, there is this rule here from Joshua Bloch, which doesn't really do it for me. You know, I still find this confusing, but it is a good rule. So producer extends consumer super. What? You know, in other words, think about it from the collection's point of view, okay? If you're a collection and you're being referenced and the type of that reference is a bounded wildcard that uses extends, well, then you can produce, yeah? You can send stuff back. On the other hand, if the reference is a bounded wildcard that uses super, well, then you can consume, okay? Things can be passed into you. So that's one way of thinking about it. A better way, which I really like, comes from Anders Hejelsberg, sorry for massacring his name there, who invented C# and TypeScript, amongst many, many other things. And again, there was a little competition on Twitter, and the competition was, what's the most difficult programming concept you can explain in a tweet? And this for me is gold. This is absolutely brilliant. So he says, okay, let's say you've got a type variable and it's typing something which is read-only. It's naturally covariant. You can get stuff out, okay? But when a type variable types something which is write-only, it's naturally contravariant. You know, you can put stuff in, yeah? But then when it's both read and write, well, then it's naturally invariant. You know, the type has to be exact. So that really summed it up nicely for me. And then the final thing, before we leave Java behind, can I do this? No, sadly not. I cannot create a new T. Or you see here, we're trying to create a static field of type T and an instance field of type T. Can I do these? Well, only one. Which one? B. I can only do B. And that's because generics on the JVM is non-reified. Okay, so again, what does that mean? Well, this is the other thing that you need to understand if you're going to make sense of generics on the JVM. So non-reified means that it's compile time only. In other words, the information that you're providing using the type parameters is used by the compiler and then erased. So I'm sure you're all familiar with the term, pardon me, type erasure. So you use T, but T usually gets replaced with object, unless you've used an upper bound, in which in this case it would get replaced with employee and so on. So another way in which it's phrased is that you've got two kinds of translation. You've got a homogeneous translation and a heterogeneous translation. So homogeneous is what you have in Java, okay? So that's where no matter what values you've given to T and how many different values you've used for T, you only get one output, okay? The other way of doing it, reified generics, is where you get a different version of the class for each use of T. So let's say we had a linked list of employee, yeah, well then the compiler would basically generate an employee linked list. You know, it would go through your code and each instance of T would get replaced with employee. And then let's say you also had a linked list of manager. Well, then it would go through your code and each instance of T would get replaced with manager. So effectively you'd have a manager linked list. And the same thing for director, you know? So if in your code you had said linked list employee, linked list manager, linked list director, well, then at runtime, what you would have is three specializations, you know, three different versions of the class. So the compiler and the virtual machine would in some way collaborate so that if you had 3 versions of T or 5 versions of T or n values for T, well, you'd get n different versions of the class at runtime, okay? And that's what reified generics means. So, of course, you don't get that for free. For example, in C++, it swells the size of your output, you know? So if you've used the standard collections and you've used a lot of different values of T, and it's a relatively small program, well, you look at the size of your executable and you go, whoa, why is that .exe so massive, you know? And that's because for every different value of T, a new version of the class actually got created. So was it a good idea to go the Java way? You know, was it a good idea for things to be non-reified and types to be erased and so on? Well, in that white paper I recommended earlier, Brian Getz makes a very strong and persuasive case for it being the right way to go, you know, that erasure and the JVM is a good way to go. And he says, look, you know, erasure in general is something that compilers do all the time, because you're going from a higher level format, the Java language, to a lower level format like assembly or bytecode or whatever. So certain abstractions get erased along the way. That's just how it works, you know. And I accept absolutely everything he says and still disagree, okay? Because I'm an educator. I only care about how hard or simple it is to teach people, yeah? And the problem is that we're not just going down, we're also going back up again, okay? So whether you're using Scala, or Kotlin or Java, well, yes, you're compiling to bytecode, but then that bytecode is loaded by the JVM, you know, and we see the JVM and the Kotlin or Java compiler as being peers, you know, of one another. They exist at the same level, you know. So anything the Java compiler knows, we expect the Java virtual machine to know. The clues in the name, okay? So the fact that stuff that the Java compiler knows is not known by the virtual machine, that causes all kinds of problems, you know? So we have a leaky abstraction, yeah? So can Kotlin help us? Of course it can, you know, otherwise there wouldn't be any point to this talk, yeah? So it can help us in 4 ways, and let's just run through them quickly. So the first of all is that we get rid of these hideous bounded wildcards. They're gone, okay? So what do we have instead? Well, we have declaration site variance. What? Okay, so let's say I'm going to write my own list implementation. Well, I can have an interface that contains the read-only operations, you know, the operations where we're only pulling out T's and doing stuff with them. And I can indicate that to the compiler by saying out T. So whenever I declare my type parameter, I can use the out keyword to tell the compiler I'm only taking things out, you know, and it will only let me take things out. By the way, taking things out to put them into a lambda, that's fine, okay? So find first and find all, that those are just fine. And then we can go the other way. So let's say I want to have like a sync. So I want to put the operations for writing into another interface. So I can do that, and I can say int. So now I'm saying that I'm only going to be passing values in. I'm not going to be pulling them out, okay? So I can have both those interfaces, and then of course the same concrete type can implement both of the interfaces, yeah? So I can have a my list that implements the read-only list and the write-only list. And then the same questions can be asked, yeah? So by the way, I'm not giving people an opportunity to answer these because I've got no way to get the answers back, and there's a delay in the video, so it would be incredibly confusing, you know? But one thing that you might enjoy doing is going through the slides for this talk afterwards and trying to answer the questions before you go on to the next slide. It's a good indication of how good your generics knowledge is. So we can write the same, we can answer the same questions in Kotlin so that the same kind of rules apply, but now hopefully it's a lot easier to understand. So instead of having to have my bounded wildcards, which I would have before, I've now got my read-only list interface, and I've got my write-only list interface, and so on. And hopefully things are a little bit more intuitive. You know, hopefully things make a little bit more sense. Yeah. So that's the idea of declaration site variance. Of course, it does depend on you giving good names to these interfaces, you know, and naming is hard. Yeah. But hopefully you can get past that, you know. So declaration site variance to me makes a lot more sense than using your bounded wildcards. But let's say, you know, we can't create the interfaces, we're working with other people's types and so on. Well, then we can have use site variance. So you see here, whenever we're declaring our function, we can use the in keyword, yeah, or we can use the out keyword, you know. So we can use the in and out on the type parameter whenever we're declaring our functions, yeah. And that does the same job as the, again, as the bounded wildcards. So an interesting example of when you might want to do this, and this is the example that everybody gives, is let's say we've got 2 my lists and they don't have read-only and write-only interfaces, but we want to take 10 items out of the first and put them into the second. Yeah. Well, then we can use the out keyword on the first and the in keyword on the second. And then you can also do constraints and generic types. So we can say T:employee, yeah. So that effectively adds an upper bound, and you can use the star to mean of unknown type. So that is the equivalent of the question mark in that case. And again, that these work the way you would expect. So much for our wildcards. What about reification? So here's a practical example of reification. Let's say we have a function that takes a list of any, and we want to filter it. So this is a generic function that takes a type parameter t, and what we want to do is we want to select only those t's. So if you look at the code, we're going to loop over all the things in input, and then we're going to do a type check. So we're saying, okay, if item is of type t, where t is the generic type, we'll then add it to the output. Okay, so will this work? Well, having built it up to this stage, you're all, of course, expecting me to say yes, but the answer is no, because Kotlin compiles to bytecode and runs on the JVM, so we're still working with non-reified generics. So it won't work unless we give some help, okay? So what we can do is we can say to the Kotlin compiler, look, I want t to be reified, okay? So every time I call this function, there will be a value for t. It could be string or customer or date or whatever, yeah? So I want a different version of the function, yeah? But of course, that's not something that bytecode or the JVM supports. So the only way that we can make that work is by inlining it. Okay, so we can say generate a new version of the function for customer or string or integer or whatever, but then inline that at the call site. Yeah, so if we do it that way, then it will work. So just to prove the point, here's some example code. So you see here, I've got my main function and I create a list of numbers and strings. And then we're calling example 1 and example 2. And example 1 uses filter by type for int, whereas example 2 uses filter by type for string. So in example 1, we only want to print out the numbers. In example 2, we only want to print out the strings. So here's our filter by type. And this is what it gets converted to. So if you haven't done it already, in IntelliJ, there's a really nice feature where you can take your Kotlin code and you can say generate bytecode. And then you can say, please reverse engineer that as Java. Okay, so I really recommend this whenever you're trying to get your head around a weird feature in Kotlin. So whenever Kotlin is performing some kind of magic for you, yeah, well then take the code that you've written, get the bytecode view, and then if you can look at raw bytecode and understand it, well done. Otherwise, hit the button on the bytecode view that will reverse engineer it as Java. Okay, and then you'll be able to see what's going on in Java terms. So you see here we've got our two functions, example 1 and example 2. So just going back, remember that example 1 we were filtering by int, example 2 we were filtering by string. Okay, and that was our filter by type function. So if you look, the code for filter by type has been embedded in both example 1 and example 2. Okay, so the loop has been turned into a while loop using an iterator object. So we're saying has next and next, and we're pulling back a value. And in Kotlin terminology, we were using the is. In Java, that becomes the instance of course. But note that in example 1, we're now saying instance of integer. And in example 2, we're saying instance of string. So what the Kotlin compiler did was it reified the function and then inlined the function call, So it's really, really good to be able to have that. And this is something that I do all the time, yeah, because I'm a huge fan of generics because I came up through C++, where templates, as they call them, are used all over the place. So I'm fairly comfortable with generics. I really like them. So here's a good example of where I was using it the other day. So I was using Spring Boot, and actually I was using Spring Webflux, so their new reactive API for writing RESTful services. And here I'm just sending a GET request to a URL. And I'm going to get back some JSON, yeah? And this JSON is going to be a list of order or customer or employee or string or whatever. That's the T, okay? So T here is the type of the thing that's coming back from the server as JSON. So for each customer, let's say in the JSON document, I want to create a new customer object. For each order, I want to create an order object and so on. So in general, I want to create a whole bunch of new T's. Yeah. So I wouldn't be able to write this code generically unless I had reification available to me. So I can declare T as being a reified type, and then I can inline it. you know. So this is the way that you'll use reification all the time, you know, in your day-to-day coding. So is Kotlin better? Of course, you know, otherwise I wouldn't be doing this talk. Yeah. So just to finish off, where might we go in the future? Okay, so we have barely scratched the surface in Kotlin and in Java of where we could go with generics. Okay, so let me show you a really interesting feature. So one of the places where they're really pushing generics to the max is inside TypeScript. They're doing lots of really fun stuff in TypeScript at the moment. And one of the things you can do is mapped types, okay? So we all know what the map function does in functional programming. You're doing a transformation, same kind of idea here. So what we're doing is we're going to take an input type, T, and we want to generate a new type by iterating over the properties of T, okay? So whenever you see the square brackets here and the P and key of T, we're iterating over the properties of T, you know, the members of T, the slots of T, however you prefer to think of it. So if I just said here P and key of T, TP, well, then I just get a type which is absolutely identical to the original, yeah? But you see here what we're doing is we're saying read-only. So I'm adding the read-only modifier, okay? So let's say T was customer and customer had 5 properties, yeah? Well, then we're going to get a new type, which is the same as customer. It has the same 5 properties with the same name and the same type. But now if they weren't read-only already, they are now, okay? So I can get a read-only version of a type. Or I can go the other way, yeah? So let's say I know that the input type has 1 or more read-only properties and I want to take those off. So I could declare a mutable T, and then in there we can iterate over the properties of T, and then we can take off the read-only flag if it's there, okay? In the same way, let's say we wanted to have a partial version of a type, okay? So in TypeScript, we can use question mark to say this property is optional. You know, this field doesn't have to be there, and it'll still count as an instance of this interface or type, yeah? So what we can do is we can loop over the properties of T, and we can make them all optional with the question mark. Or, yeah, we can take that off. We can make them all mandatory by saying minus question mark. And then it starts getting weird, okay? Because we can change the type of the property if we want. So I'm sure everybody on this call has had the horrible experience in Kotlin or Java or Scala or whatever, where you've got multiple trees of objects. So let's say you have a well-designed customer type, but then you're receiving customer information from the UI or the RESTful service or whatever, and everything's going to be strings, yeah? So you have to write stringly typed code. So you had your customer class with 5 well-typed fields, but now what you need to do is declare a new class the same as customer, but where everything's string, you know, and that's where you're going to load the data from the UI or the RESTful service or whatever, yeah? So it's going to be a terrible, terrible maintenance nightmare if you have like 100 entity types and you want 100 string versions of those, yeah? Not if you generate them. So you see here, I could say stringify of customer, and then loop over all the properties and change the data type to string. Okay. There's only one problem with that, which is that properties in JavaScript and TypeScript can be either fields or methods, okay? So if there were any methods in the type, they'd be changed to string as well. Don't want to do that, yeah? Well, the good news is that in mapped types, you can do conditionals, yeah? So again, I can loop over all the properties, but now I can say, okay, yeah, if the type of this property extends function, then leave it alone, okay? So just convert it to whatever it was originally, yeah? Otherwise, convert it to string. So let me just show you that in action. So you see here, I've got a person type and a customer type. So person is going to have name, age, and married of type string, number, and Boolean. And customer is going to extend person and add a method called make order. And then I've got some demo functions. So I can test a regular person. Of course, I can change the name to Dave. But let's say I've got a function that takes a read-only of person. So I will be able to pass in a person object, but I won't be able to change the name. You know, I'll be forbidden from changing anything in input. But what I could do is I could call test mutable, yeah, because test mutable takes a mutable of person, okay? So if you like, I've converted away the read-onliness, yeah, of the person object, and now I'll be able to go in and change it. Or I can write a function that takes a partial customer. And then here's an interesting example of stringify. So let's say I've got this variable called customer, which is of type stringify customer. In other words, it has the same number of properties as a customer object, and those properties have the same names, but now they're all of type string, okay? So you see there, I can go through and I can now set them all to string values, okay? The only problem is that for the make order function, it's now a string as well. Oops, okay? So what we want to do is we want to say stringify fields. So now what it'll do is it'll say, okay, this type is the same as customer, and all the properties that are fields, well, their data type has changed to string, but all the properties which were methods, well, then they have been left alone. So they will have the same parameters and return type as they did in customer. Yeah. And then there's a little demo there to just call those functions, and this is the output that you'll get in the browser. Yeah. Just to call your attention to one nice little bit here, you see I can say partial person. This is an object literal in TypeScript. So we're saying, okay, this is an object that has a name and an address. Okay, sorry, a name and an age even. Yeah, and it's not a person because it's missing the married property, but it is a partial person. It's like a subset of the person type. So I can call test partial and pass in my partial person, and that will work just fine. Okay, so you can go out and play with this now. And there's a term for this. This is called type-driven development, okay? So this is the new TDD, okay? So you're all familiar with the old TDD, test-driven development. There's the new TDD now as well, which is type-driven development, yeah? So if you want to get into this, the most accessible way I'm familiar with is start playing with a little bit of TypeScript. And there's this library called the TS toolbelt, and it contains a whole pile of these types built in, yeah? But of course, it's even more fun to go out and write them yourself. And they're continuously adding new functions to do this kind of thing in TypeScript. So you see there, one just got proposed just the other day, you know, so there's one where we're doing this kind of thing in tuples, and that will be coming to the next version of TypeScript. So what have we learned? You know, so we've gone through 3 different acts. So first of all, we've seen what the problem is in Java terms. Then we've seen how Kotlin makes your life a lot easier. And then we've seen what's possible, you know, the ways that the JVM languages could be extended in the future. So just to sum up, first of all, generics deserves a lot more respect than it gets, okay? So generics is a programming style in its own right. It's at least as complicated as OO and FP, you know? So whenever you're teaching other people to program, I strongly recommend you spend as much time on generics as on OO and FP, you know? Give it the respect it deserves. And then FP works perfectly with generics, but it's complicated with OO. You know, flat classes are fine, inheritance is not. And then Kotlin makes it much simpler. You know, Kotlin learned from the mistakes of Java and the bounded wildcards and so on. So declaration site variance and use site variance and the in and out keywords and so on, they're great. You know, so if I was teaching somebody to code in the JVM, I'd go straight to Kotlin if at all possible. And then you don't need reification. You know, Java has proved that. So you can do generics without having reified types, and it'll still be incredibly useful and productive. However, yeah, reification is very convenient. You know, this ability to say new T and so on, well, that opens the door to all kinds of other possibilities. Yeah. And then finally, there's a lot more to generics than you think. Okay, so what we think of as generics on the JVM, that's only like chapter 1. Okay, there's a lot more fun things we could do with generics, and perhaps some of these will get added to the JVM in the future. Cool. So that's my show. That's all the stuff I wanted to cover. So the slides will be made available after the talk. Please feel free to have a look and to reach out to me if you have any questions.
Okay, there are no questions. Oh, yeah, okay. Just been popped up into the slide. So thanks.
Yeah, so there is one question if I answer it, yeah, which is, could TS-like features be implemented in the JVM without runtime reflection? That's out of my league, but I'm going to say yes, because TypeScript at the end of the day just generates regular JavaScript. Yeah. So if the TypeScript transpiler can do it, then I assume that the Java or Kotlin compilers can do it as well. Okay. So I'm not completely sure, but my instinct would definitely be yes.